Hello everyone. Thank you for staying so late to hear my presentation. I really appreciate it. My name is Dusan Vuckovic and I am doing my PhD on the Technical University of Denmark. And today I'm going to show you one of part of my research that is an ultra-low power management circuit for nanowatt and microwatt energy harvesters. So the idea why even to look, so the outline, first I'm going to talk a bit of the motivation, the goal that we wanted to achieve, approach we took, how it was implemented, measurements, future work, and the conclusion. So the motivation is first looking at low sampling rate applications. Applications where we actually don't need data every second or even maybe every minute, but applications where measurements every hour or every 10 or 15 minutes are sufficient. For example, detecting of leakaging, deformations, vibrations, or operation of some devices. We had an application where we actually just needed to determine if the device is working or not. So, and also applications where the temperature is changing very slow. There are also other applications that could benefit from very low sampling rates, such as detection of gases or other environmental variables that are changing at a very low rate. Also, looking into low microwatt and nanowatt can allow a smaller scale harvesters or use the harvesters in environments that have a very small amount of energy. Here is a picture. I don't know if you can actually see the solar cells, but they're held there in a 2 lux environment where we have power in nanowatt range, and yet we were capable of providing measurement every 10 minutes of the temperature in the room, even on those light levels. So the idea was to design a power management circuit, but primarily based on off-the-shelf components, and yet be still able to operate in the nanowatt range. Also, we were looking into capacitor-based storage. So there is a possibility of having a very long deployment times, because the battery is not going to be an issue. So the main idea is to minimize the power consumption during the charging process of the capacitor, and thus making the system more energy aware. And we actually wanted to see if we can use the microcontroller for something more than just a simple load that is waiting for the power management to charge enough the circuitry and then turn it on. So in typical applications that we usually see, we have the harvester, we have the power management, and then we have some node connected and doing all the work. So we wanted to see if there is any way of actually involving the microcontroller, because the microcontroller has all these neat peripherals and A to D converters and all the other options and things that you could use in a power management application. So typically there is a power management circuit in these power levels. For example, the analog device is EH300, but the problem is that it has fixed thresholds and it cannot adapt based on your current power needs. For example, if you want to change the sampling rate or you want to do a different calculation in order to dynamically adapt the current application, these circuits cannot provide something like that. And also there is an issue because there is a fixed threshold for the high voltage value where the hysteresis turns on. The problem is that the source might not reach. So this is the output of the EH300, so the load is actually active only in this period of time. However, so it's relying on the fact that it's being charged afterwards, again to the point of VH. However, that's sometimes not the case, especially if you have a varying environment. In case of, for example, indoor solar cell use, where you can have different light levels depending on the environmental lighting. So the idea was to look at the entire physics of the process, because we have very long charging times, and does it actually make sense to monitor the capacitor voltage and do the power management all the time, but when we know that it's going to be minutes between two activations of the sensor node? So the idea was to reduce the number of analog circuitry and move the entire decision-making process into the microcontroller. So this is the approach that we took. We have a startup stage. It's going to allow us to charge the buffer capacitor to the level where the main stage will operate within the specified voltage range. And we have the microcontroller controlling back the switch for turning the system on and off, and controlling the voltage detector that we want to disconnect once the main stage is active. And as you can see, we've been using off-the-shelf components that are very easily obtainable. All of those are bought for like DigiKey. So the problem of obtaining components is not an issue. And for sensing, for this demonstration, we just used a simple NTC thermistor. So in order to get the microcontroller to work, we first have to be able to charge the buffer using a nanoamp source. And usually the problem with voltages above like 1.5 or 2 volts is that most of the circuitry that can be found off the shelf has current consumption similar to shown in this graph. So this is a, you can say, nanowatt circuit, but only above 1.5 volts. So there is a need to actually have a low leakage circuit that is going to charge the input capacitor to the point where the rest of the circuit can continue working in low power. So we designed a stage based on a circuit that's previously been published, and this stage is capable of collecting up to 3.6 volts, depending on the threshold selected, with under 50 nanoamp of total leakage currents when the system is realized on a PCB. So that's going to enable a stable operation of the subsequent stages. And what is interesting about this stage is that the threshold voltage is actually based on the forward voltage drop of the LED that's used as a voltage reference. And also the switches are realized using a low leakage analog switch. So this is the startup stage circuit. It's based on the Novotel circuit, and as you can see, this is mainly constructed out of BGTs and several resistors, making it very easy and very cheap to implement in any system. And the threshold is actually defined by the LEDs here. So depending on which color of the LED you use, you can actually select the threshold voltage. So the startup stage is going to turn on the XOR circuit. And for the XOR circuit, we're using a 7.4 AUC series, which is very low leakage, and it operates in nanoamp range if the input voltages are tied properly to the supply rails. So this allowed us to actually completely disconnect the load while the input has been charged. And once the voltage detector activated the XOR circuit, the microcontroller could actually then keep the stage active and disconnect the voltage detector, reducing the power consumption. And here, because during the startup stage, it's critical that there is no leakaging, because on the output, we want to have nanoamp current consumption. So use of typical MOSFETs would actually induce high leakage currents, even though we were working on 0.3, 0.4 volts. So we had to find an analog switch that actually operated at very low voltage levels before the XOR circuit starts up and continues operation. So after that, we actually now have the power management stage operating, and the microcontroller can be controlled using the RTC. And for the RTC, we selected a new generation of Abracon 18000 series, which has a 15 nanoamp current consumption when operating on an internal RC oscillator. This allowed us to drop down the power consumption during the sleep drastically, waking up the microcontroller only when we actually want to perform A to D conversions. So we have two operating scenarios, one where we're putting the microcontroller to sleep, retaining the memory, and the other where the RTC is actually completely removing the supply from the microcontroller. So in the sleep scenario, data is retained, allowing us to do more advanced power management and more advanced energy-aware operation. There's no need to reconfigure the RTC on every wake-up cycle. It's a very fast wake-up cycle, but it has a higher power consumption. While in the off scenario, the RTC is completely disabling the MCU. It has a longer startup time, which then in turn has a longer power consumption. However, this is compensated, on the other hand, by very low average sleep currents. And it gives us the same operation as a typical energy harvesting power management, where the microcontroller is turned off during the harvesting stage, during the energy collection. So we first modeled the entire operation. So the power of the RTC, as you can see, is 25 to 50 nanowatts. Energy required for the microcontroller to perform one A to D conversion and do a selection of the further behavior based on the measured voltage was 50 nanojoule. And the energy required to start up the microcontroller, do the measurement, and perform the reconfiguration of the AD of the RTC was 1.4 microjoule, and the sleep current is 250 nanowatt. So if we want to do a wireless measurement and based on this power management, you can see how long it's required to sleep in order to charge a capacitor, enough to do the measurement. And here you can actually see how big the power consumption is based on how long the sleep period is. And as you can see, if we have current input currents that are in the range of 0.2 to 0.5 microamps, we need sleep time of around 100 seconds. And for sleep times of around 100 seconds, the power consumption of the power management stage is around 50 nanowatts. And here, for example, we have a comparison between two sleeping scenarios and a top of the line off-the-shelf comparator. And as you can see, very fast, it becomes more efficient to actually use the microcontroller and do the ADC than to actually have a dedicated comparator operating using the off-the-shelf comparators. So in the end, we actually have sleep times that we can adjust because we can measure the voltage. We know how much energy there is in the storage and what we can do depending on the application, allowing us a better power management stages and control of the energy. And in the future, we're going to add an FRAM module so we can store the data in order to improve the algorithm for waking up and determining the wake-up period. And with that, I would like just to conclude and thank you all for your attention. Over for questions.